welcome to today's class. So for today, we're looking at how to calculate the atomic mass or the atomic weight of elements given their isotopes. One thing you should notice this: in chemistry, the term mass and weight are used interchangeably. Of course, if it was physics, if I'm given mass, I'll have to convert it to weight by multiplying with 9.81 or 9.8 as the case may be. But in chemistry, we don't consider that, okay? So in chemistry, mass and weight are used interchangeably as being the same thing. Alright, so how do you calculate the atomic mass or perhaps the atomic weight of an element given the isotopes? How do you do that? Now, the formula is simple. We only have to sum the product of the fractional abundance, also called percentage abundance, by the mass of the individual isotope. It's that simple. So this is how it's done. We're saying that the sum to calculate the atomic mass or atomic weight of an element, my atomic mass or atomic weight is equal to the sum of the fractional abundance of an isotope multiplied by the mass of the isotope. Alright, so I have this. So this is how we solve this. Alright, so this is for each of the isotopes and then we combine them. That's the formula. We'll take a simple example here and we'll solve it. This example says bromine is composed of bromine 79 having 78.9183 AMU. AMU that means atomic mass unit, okay? So AMU there is equal to atomic mass unit. It's the same as saying gram per mole. That's the same thing we use in molar mass. So AMU and gram per mole are the same thing, alright? But AMU then means atomic mass unit. Alright, let's proceed. So we said bromine is composed of bromine 79 that's having 78.9183 AMU and bromine, is that supposed to be bromine, not beryllium, please? Bromine 81, that's 80.9163 atomic mass units. The percentage composition of a sample is 50.69% for bromine 79 and 49.31% of bromine 81. Based on this sample, calculate the atomic weight of bromine. Alright, so let's get this done. So, solution, let me list out given parameters. Number one, they said bromine is composed of Br79 as 78.9183 AMU. So the mass, so the first thing I'm doing there, number one, the mass of bromine 79, they said is equal to 78.9183 AMU. Also, they said, and number two, mass of bromine 81, that's equal to 80.9163 AMU. Alright. Is that the percentage composition of a sample of bromine 79? Number three, percentage composition of bromine 79, Br79, is equal to 50.69%. 50.69%. Now we have to convert this. This is equal to 50.69 all over 100. That's percentage. That will give you 0.5069. So I have this Finally, number 3. Number 4. The percentage composition of bromine 81 is equal to 49.31%. Alright, convert this to I'm having 49.31 all over 100. That's equal to 0.4931. So I have this. So it's as easy as this, okay? So get the mass for each of them. Also get their percentage composition. Alright, if you're done with this, now let's solve this question. Right, so for this case now, recall that atomic weight is equal to sum of fractional abundance of, since I'm using percentage, so percentage abundance. So percentage abundance of isotope multiplied times the mass of isotope. So I have this for each of them. So we have for bromine 79 and bromine 81. So let's apply this to each of the isotopes. That's equal to the first, there are two isotopes here, bromine 79 and bromine 81. So let's start with the first one there. Percentage abundance of bromine 79 times the mass of bromine 79. This plus percentage abundance of bromine 81, yeah, times mass of bromine 81. So I have this. So this is equal to percentage abundance of bromine 79 is this. That's 0.5069 times mass of bromine 79 is 78.9183. That's for 79. Plus, let's get for 81. For 81, I have percentage composition of bromine 81 0.4931 times mass of bromine 81. Bromine 81, the mass is 80, so 80.9163. So I have this. Alright, so this is now equal to 0.5069 times 78.9183. That's 40.003. 4 decimal places 0037 in 4 decimal places plus, let's multiply this one here, 0.4931 times 80.9163. That's about 39 points. In 4 decimal places I have 8998. Alright, so if I sum this, it means that atomic weight of bromine, so hence atomic weight of bromine is equal to, I'm having 40.0037 plus 39.8998. That's about 79.9035. Atomic weight is in AMU. So I have this as the answer. So this becomes the answer to the problem. In most cases, you'll be asked to provide the answer in 1 decimal place. In 1 decimal place, this gives you 79.9. So you stop there. Alright, so this is how we solve this question. Alright, so let's look at another problem there, another sample question that says, calculate the atomic weight of silicon using the following data for the percent natural abundance and the mass of each isotope. So in the first thing, there is silicon 28, having a mass of 27.9769 atomic mass units, having a percentage of 92.23%. Also have silicon 29, having a mass of 28.9765 atomic mass units and percentage composition of 4.67%. And finally, you have silicon 30 with mass 29.9738 atomic mass units, having a percentage composition of 3.10%. Alright, so we have to calculate the percentage weight of silicon. So I'll just go straight to the solving. I've demonstrated how you arrange your question in a previous example, so I'll go straight to the solving. So for this, we say atomic weight of silicon is equal to the sum of the fractional or the percentage abundance of each isotope multiplied by the mass of each isotope. So this is equal to, let's start with silicon 28. The percentage abundance is 92.23%. Divide by 100 to convert it to decimal, it becomes 0.9223. So that's just divide that by 100 multiplied by the weight is 27.9769 plus, let's look at silicon 89. The percentage is 4.67%. Divide by 100 gives you 0.0467 times the mass of the isotope is 28.9765 plus the next one there is silicon 30, having 3.10%. Divide by 100, 0.031 multiplied by the mass there is 29.9738. So I have this one here. So the task is very simple. For each of them, convert from percentage to decimal by dividing each of them by 100. Then when you're done with that, multiply by what? The atomic mass or the mass of each of the isotopes. Please match them correctly. And that's all. So let's get this man solved and see our answer. By the way, you can keep in place. This was for silicon 28. This is for silicon 28. This is for silicon 29. This is for silicon 30. So if I include values, this is equal to, I have 0.9223 times 27.9769. So that's about 25.8030, or let's say 31 to 4 decimal places, plus for silicon 29, I have 0.0467 multiplied by 28.9765. That's 1.3532 plus 0.031 multiplied by 29.9738. That's about 0.9292 approximately. So if I add this up, this will be equal to 25.8031 plus 1.3532 plus 0.9292. That's about 28.0855. Convert this to perhaps one decimal place, or let's say two decimal places, gives you 28.09 atomic mass units. That's approximately in the nearest whole number. That's 28 atomic mass units. So this becomes the weight of silicon. So this is how you solve this. All right. Let's take one more example on this, and then we proceed. So let's look at this question. This question says the atomic mass of gallium is 69.72 atomic mass units. Full stop. The masses of the naturally occurring isotopes are 68.9257 atomic mass units for gallium 69 and 70.9249 atomic mass units for gallium 71. What is the percentage abundance of each isotope? Now, in this case, now observe that we've already been given in our previous examples, in our first two examples, we are asked to find the atomic weight of the element. In this case, we are now given the atomic weight of the element and now asked to find the fractional abundance. So how do you solve that? First things first, let's list out giving parameters. Let's list out given parameters. So solution, given parameters, they said the atomic mass of gallium by 1, and given atomic mass of gallium it's equal to the value again is about 69.72 atomic mass units. So I have this. Next, we said the mass of the naturally occurring. So number 2, I have the mass of gallium, what there? Gallium 69. The value is 68.9257 AMU, and also number 3, we have the mass of gallium 71 as 70.9249 AMU. So I have these parameters just to be sure. Alright, so this is what I have. Alright, so we have to find the percentage or the fractional abundance. Now we look at the fractional abundance of gallium 69 in decimal multiplied by this value, its mass, plus the fractional abundance of gallium 71 multiplied by this value, which should sum up to give us this. And the question we asked to find is what is the percentage abundance of each of them. So how do we find it? Now, to get this answer now, let us go back to our previous two examples. In our first example, we dealt with bromine. We said bromine had two isotopes, which were bromine 79 and bromine 81. Look at the value of the percentage abundance in terms of decimal for bromine 79. The value was 0.5069 for bromine 79, and the value was now 0.4931 for bromine 81. If we combine this, what do you observe? 9 plus 1 is 10, 0 carry 1, 6 plus 3 is 9 plus 1, 10, 0 carry 1, 9 plus 0 is 9 plus 1, 10, 0 carry 1, 5 plus 4 is 9 plus 1, then 10, 0 carry 1, 0 plus 0 is 0 plus 1, 1. If I combine the different fractional abundances, I'll have 1. Let's look at the second example. For the second example, where we did silicon, we said the silicon had 3 isotopes. The first one was silicon 28, whose isotope had a fractional abundance of 0.9223, plus silicon 29 had a fractional abundance of 0.0467, And then silicon 30 had a fractional abundance in terms of decimal. Please check your work. It was 0.0310. Combine this. These two gives you 10. 0 carry 1. 2 plus 6, 8 plus 1, 9 plus this one here, 10. 0 carry 1. 2 plus 4, 6 plus 3, 9 plus 1, 10. 0 carry 1. 9 this, that's 9 plus 1, 10. 0 carry 1. Dot 0, 0, 0 plus 1, 1. So observe that if I combine the value of the percentage abundance of all the isotopes, it will give you 1. So what does it mean here? It means that for here we'll make an assumption. We say let the percentage abundance of let me divide this here, of the first one here, gallium 69, gallium 69 be equal to X. So we say let the percentage abundance of gallium 69 be X. So also let the percentage abundance of gallium 71 be, let's say, Y. Now from what we did earlier, we said if I combine the value of the percentage abundances of each of the isotopes in terms of decimals, that our result will be 1. So hence, it means that this value X plus this value Y should be equal to 1. From here, let's get the value of Y. From here, Y will be equal to 1. X comes over and becomes minus X. So I have this. So you can say equal to Y and say Y is equal to 1 minus X. So hence, we can say that the atomic mass of gallium, this, is equal to X, which is the assumed value for the percentage abundance of gallium 69 times the mass of gallium 69 plus Y, which is the assumed value of the percentage abundance of gallium 71 times the mass of gallium 71. Alright, let's solve this and see what we have. We said atomic weight of gallium is equal to the sum of the product of the percentage abundance of isotope times the mass of the isotope. So I have this. Alright, so having said this, let's input values. The atomic weight of gallium, my question here was 69.72 is equal to, let's start with gallium 69. For gallium 69, the fractional abundance we said was X times the mass of gallium 69 in the question then is 68.9257 plus, let's look at gallium 71. For gallium 71, we said the percentage abundance was Y, which in terms of X was 1 minus X, as we had. Okay, and then now this was the percentage abundance of gallium 71 as we did. Then the mass of gallium 71 was 70.9249. So we have this. Alright, so let's solve this. So this gives you 69.72 is equal to X times this is 68.9257X plus this times 1 is itself 70.9249. This times minus X gives you minus 70.9249X. So I have this. Alright, our task will now be collect items, move this man over here, becomes 69.72 minus this one plus comes and becomes minus 70.9249 0.9249 is equal to this value 68.9257x minus this value minus 70.9249x. So I simply move this one here over to this side. The plus became minus, that's all. Alright, let's solve this one here. 69.72 minus 70.9249, that gives minus 1.2049 is equal to, this value is 68.9257 minus 70.9249, that's minus 1.9992x. So I have this. Alright, so divide here. To get x, divide here by this coefficient minus 1.9992. Divide here by the same coefficient minus 1.9992. So minus cancels minus, this cancels this. So therefore x is equal to, so let's get this, this will cancel this, so I'm left with 1.2049 divided by 1.9992. That's about, in 2 decimal places, that's about 0.60. So I have this as the percentage abundance of gallium 69 in decimal. Alright. So therefore, the percentage abundance of gallium 69, which is x, is equal to 0.60. Our next task will be to convert it to fraction. If you observe our first two examples, the percentage abundance were first given in terms of percent before we converted to decimal. So in this case, I'm having it as a decimal, convert it to fraction, or perhaps convert it to percentage. What do I have? This is equal to, simply multiply by 100 times 100. This is equal to 60%. Alright. Now, the percentage abundance of gallium 71, that's why we said is equal to 1 minus x. So this is equal to 1 minus x is 0.60. If I do 1 minus 0.60, it will give you 0.40. And of course, to convert this to percentage becomes times, that's equal to 0.40 times 100, and that's equal to 40%. So therefore, the percentage abundance of gallium 69 is equal to 60%, and the percentage abundance of gallium 71 is equal to 40%. Alright, so this is how we solve this question. So that's our answer.